Hello everyone. Today we will discuss some very basic things about linear optimization, including some graphical insights and motivation for the simplex method by looking at some examples in 2 dimensions. So recall that a linear programming problem LP for short has 2 different forms that we can use. One is the general inequality description, which is of this form ax less than equal to some vector h more than d, and I am trying to minimize C transpose x, and x is between some upper bounds and lower bounds. Inputs given to us are the vector c, d, h, l and u. A different form is what we call the standard form, the objective function is the same, C transpose x, subject to ax equal to b, x greater than equal to 0. So here the inputs are a, b and c. The standard form is particularly useful from the point of view of algorithms. In particular, the simplex method that we will talk about in the next class, and this inequality description is usually useful in understanding the geometry of how these methods work and what are certain properties of these optimization problems. A simpler form of the geometric general geometric form is a simpler form. Many books may also call it a canonical form. And it is of the form minimize C transpose x, ax greater than equal to b. So let's call this form 3. Let's call this general inequality form as 1 and the standard form as 2. So all 3 forms are identical or equivalent. It's easy to convert any LP in form 1 to form 2 and form 3, and also vice versa. So given any problem in any of these 3 forms, one can always convert it into the other two forms. And have the same equivalent problem in the different form. So that makes our life very interesting, because depending on what insight we want, and depending on which part or which aspect of the algorithm or the theory we are looking at, we can use a convenient form and then try to get a good understanding and intuition behind it. So let's do an example of an LP in a canonical form, so that we can get some geometrical insights. So let's take an example. Minimize minus 4x1 plus x2 subject to 2x1 plus x2 less than equal to 10, minus x1 plus 2x2 less than equal to 10, x1 less than equal to 4, x1 minus x2 less than equal to 3, x1 greater than equal to 0, x2 greater than equal to 0. So this example is not in any of the three forms that we talked about in the previous slide. However, it's easy to convert it into any of the forms that I want. So for example, if I want it in the canonical form, that means simple inequalities of the form ax greater than equal to b. So then I would have so I just multiplied both these inequalities by negative of 1, so that the sign of the inequality changes and I get the canonical form. The last two inequalities are already in the form that we want, so we are not going to multiply them by anything. Okay. So let's say this is inequality 1. So this is inequality 1 into minus 1, and so on and so forth. It's also easy to write it in the standard form. All I need to do is add some slack or surplus variables to make all general constraints as equalities and all variables as non-negative. So I will get x1 plus x5 equal to 4, and x1 minus x2 plus x6 equal to 3, and xi greater than equal to 0, I equal to 1 to 6. So notice that we have added all these are my slack variables. Had my constraints been of the form greater than equal to, then I would have needed surplus variables. And this standard form is the form that we wanted, where Ax equal to b, all general constraints are equality constraints, and then I have some more inequality constraints in the form of non-negativity of the variables. Okay, so so if I'm able to solve the problem in any of these three forms, I will be able to get the solutions of all other forms also very easily, as these forms are all equivalent to each other. Let's try to solve this example geometrically and see whether we can gain some insights out of it. So first of all, since my original problem is only in two variables, I can try to plot the objective function and the feasible region of the constraints graphically. Let's see if we can do it. So this is my x2, this axis is x1, and let's say 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6. If I look at my first constraint, it is it's a region marked by this line, somewhere like this, and this is my constraint 1. So everything below this line is the region defined by this constraint. Similarly, I can draw the constraints for all other inequalities. So let me just draw the most simplest one first. So actually this the first one is somewhat down below, it hits us somewhere here. This is obviously approximately drawn. So let me just label them so that it's easy to see or what these constraints look like. So this is constraint number 1, this is constraint number 2, constraint number 3 is this vertical line, and the 4th constraint is this, and each constraint is asking us to be on one side of the corresponding line. And I also have these non-negativity constraints, so x1 greater than equal to 0 means I need to be on the right side of the y-axis, and x2 greater than equal to 0 means I need to be above the x2 equal to 0 line. So if I look at the intersection of the feasible regions of each hyperplane, I will get the feasible region inside this polyhedron. So this is the set of all points allowed by my constraints, and within this region we would like to find the point so that the value of the objective function is minimum. So one way to find such a minimum point is to try to sample many points. So just select, by hit and trial, try to find as many points as possible in this region, evaluate the objective function and pick the best. But that is quite ad hoc and unsystematic. We would like to have a good algorithm which gives us the definite answer every time. So the methods that we will talk about rely on this idea of the corner points. So I can find these corner points rather easily for this example. This is 5, 0, 5, 2, 6, 4, 2, 4, 1, and 3, 0. So if we want to geometrically solve this problem, we can start from any point. Let's pick the red point. Let's say this is x0, and let's take a simpler point. Let's take a point 1, 1. So consider it is feasible because it satisfies all constraints, and the objective value is -3, and the point is somewhere here. If I want to find other points that have the same objective value, I can try plotting the contours of the objective function. So the contours of the objective function are the lines or the areas where the objective function has the same value. So with a little bit of thought, it is easy to see that a line of roughly this shape will have objective value -3. Okay, so you pick any point on this line. This is so now if I want points with better objective function value, then I can try to move this line in some direction. I can start going slightly towards the right hand side and move to -4x1 plus x2 equal to -4, and for example the point 1, 0 actually lies on this line. So clearly this 1, 1 is not an optimal point. I can move to the right and get better points. So and it's easy to see that I can keep moving until I hit some sort of a boundary of the feasible region, which prevents me from moving any further. So this point would be -4x1 plus x2 equal to -15, and it is geometrically, if I want to go to a even lower value, then the contour corresponding to even lower values will never hit the feasible region, and that means that really this 4, 1 is the optimal value. And the objective value at this point is -15. Note that in this case the optimal solution is unique.